Relative velocity, type 1, shortest distance, C, visibility. So here in 2002 we were given two boats, B and C, which are moving with constant velocity, and we're told that at a certain instance boat B is 10 kilometers due west of boat C, and we're given the speed and direction of boat B relative to C is 2.5 meters per second in the direction of 60 degrees south of east. So rather than being given the individual velocities of both B and C, we're only given the relative velocity this time. So we don't have to work that out, but what we do have to work out is our I and our J components of that, because 2.5 meters per second, we're given it in terms of our mariner's compass rather than in terms of the resolved I and J vector component. Once we have that, then we have to calculate the shortest distance between the boats, and we have to be careful to do that in the nearest metre. So we're going to start by setting up our diagram showing what this actually looks like. So we have to be careful. It's B relative to C, and it's B due west of boat C. So that means that B is going to be on the west of C. And we're also going to be marking in the fact that they are 10 kilometres apart. Now, the fact that our speed is given to us in metres per second, I'm going to write down my distance in terms of metres. So that's 10 kilometres, in other words, 10,000 metres apart. And then we're going to put our mariner's compass at B, because then we're told that it's B relative to C and it's in a direction of 60 degrees south of east. So southeast, this direction here. So that's the velocity of B relative to C, and the angle then is 60 degrees. Okay, so the shortest distance then, if I mark in on my diagram, is always our perpendicular distance from C to the relative path. That is obviously 90 degrees. So therefore this will be D, and this will be X, where D is our shortest distance, and X is the relative distance along the relative path. And then if that's 60 degrees is opposite D, D will be the opposite. 10 kilometres is opposite the 90 degrees, so that's the hypotenuse, and our relative distance is X. Okay, so what else can we mark down? Well, I'm given the fact that we have to work out our I and our J components because we don't know what our magnitude, no, we do know the magnitude, sorry. So the fact that we already have our magnitude, I don't need to bother with that. So we have to work out our shortest distance first of all. So part 1 is our shortest distance. So that's DH sine theta, because of course sine is your opposite over your hypotenuse. And therefore our hypotenuse is 10,000 metres, so 10 kilometres. And our sine theta is going to be sine 60 degrees. And sine 60 degrees is root 3 over 2. So therefore root 3 over 2 times 10,000 gives us, that's 5,000 root 3. And of course to the nearest metre is what they want. So to the nearest metre will be 8,660 metres. So we wouldn't get marks for leaving it in terms of surd form for this question. Okay, so the second part of the question then says calculate the length of time, and that's to the nearest second, for which the boats are less than or equal to 9 kilometres apart. So the fact that we know that our shortest distance is 8,660 metres, the fact that they're going to be less than or equal to 9 kilometres apart means that it must be to the left and to the right of this. So that could be 9,000 metres. and that could also be 9,000 meters. In other words, essentially what we're doing is we're drawing a circle of radius 9,000 meters. So this is our 9 kilometers. So essentially what we've created here then is two right angle triangles that are congruent. They're exactly the same. And what we can work out then is this distance, which is the base here, y, and that will also be y. So in other words, the distance between these 2 points would actually be 2y. And that would be the relative distance that they are 9 kilometers apart from each other. So if we draw out a separate triangle here to show that, it becomes very apparent what we need to do in order to solve this. So we have 8,660, and then the hypotenuse is 9,000, that's meters. And then y is our base. So if we're doing Pythagoras, we have our hypotenuse and our opposite and our adjacent. So by subbing in there, I can get the adjacent, which is, I'll change that to y, is equal to the square root of then 9,000 squared minus 8,660 squared. And therefore that gives me y is equal to 2,450 meters. So therefore if I double that, that gives me 4,900 meters. So in other words, what we're saying there is that the relative distance when they are 9 kilometers apart is going to be 4,900 meters. So of course we want to know then, well, how long are they going to be visible for? So therefore to get our time, we know that our relative speed will be equal to our relative distance over the time taken. So therefore the time will be 4,900 divided by, if we go back, what was our speed? Was 2.5 meters per second, and that's our magnitude because it's our relative velocity from B relative to C. So that's 4,900 divided by 2.5 meters per second, which gives me 1,960 seconds. And again, that's to the nearest second there. So really, really, really nice question that year, and it was 25 marks. So if we're looking at the breakdown of marks, where they were going for, so we got 5 for setting up our shortest distance and 5 for getting it correct to the nearest meter. And then we had 5 for working out one of the relative distances, in other words, the y. And then we were getting 5 for setting up our time equation, and then 5 for actually working out the time correct to the nearest second. So really, really, really nice question, that 25 marks. So we always like the nice ones.